Hello, everybody. It's a great pleasure and it's a great honor to be among the speakers on this special occasion. The older people among you should know where I borrowed and adapted this title from. Everybody else needs to Google it and do watch the movie. So what I'm going to do is I'll give you a tour of my own scientific journey over the last 30 or so years. I started in database systems, but then I went into web research with a strong AI flavor. But I've revisited the database area once in a while. And as we go along in this journey, I will also point out connections to Martin Kersten. So database systems first. In the 90s, I worked on what I called self-tuning systems with performance guarantees. This slide gives you an example. We consider a set of files characterized by their size and their access load or heat, and we have to place them onto a parallel disk array or distributed storage system so as to balance the load. One technique is to partition the data, and then the actual allocation step. The result could look like this. And then when we measure the access load, we get a nicely balanced system, very good performance, but nothing lasts forever. The workload changes over time. So this file, for example, might get hotter and then the disk becomes overloaded and performance degrades. So the countermeasure is to migrate it to a different disk and rebalance the system. This can happen again, and now this file causes an overload on this one disk. So another technique is to split the file on the fly and move only one of the partitions for more fine-grained countermeasures. So we thought this was a really cool method, and hence we called it disk cooling. But it was only moderately successful, didn't have any notable impact. In hindsight, I think it was because we addressed it at the wrong level of abstraction. At the file system level, there's much simpler approaches, for example, coarse-grained striping across all disks, and these do the job. However, 15 years later, these people, led by Martin Kersten, came up with this cool database cracking method, more advanced, more powerful, and they applied it to the right level of abstraction, namely relational database tables, which is something that query processing and query optimization understand and can thus exploit. And we all know that between a good and a bad execution plan, there could be orders of magnitude difference in performance. In the 2000s, I became interested in the web. This slide shows you that back then, databases and the web were two totally separate universes. Databases were crisp in various dimensions. Web was all fluffy. People shied away from this. The applications, on the other hand, in the database world, I always thought of them as very boring. It's all about suppliers and parts, inventory, payroll, and so on. And the exciting things are on the website. So around 2004, I gave myself this mission and vision: bring database assets to web contents, enhance search engines and the understanding of web contents. The first theme we pursued was structured queries over web contents with ranked results, mostly by imposing XML views on the web page contents. That was a mixed success story. But then we varied the theme and we thought of going for an intermediate layer first, a comprehensive knowledge base automatically extracted from the web, capturing entities and relationships between them, and thus being able to support and boost the quality of search engines. So machine knowledge from the web. This is the main part of the talk. One way of introducing this is by means of search engines, which is a major use case. This shows you a search engine 10, 12 years ago without any underlying knowledge bases or knowledge graphs, as industry calls them. I query for Martin Carsten Awards. I get back 10 blue links with good quality pages, but I have to go through them, sift through them, browse back and forth. 30 minutes later, I have what I wanted to know, but it's tedious. This has changed because now all the search engines have a major knowledge graph as a background asset, invisibly working to end users, or at least often invisibly. Here it's actually implicitly visible, because on top of the 10 blue links, you get these crisp results, excerpts from the knowledge graph, which give you concise and precise entity level answers. We can do this with searching about a given entity, or we paraphrase a set of entities, like giving the description of a semantic class, and again, good results. And we can go even further. Question answering, full-fledged question answering is supported as well by search engines and also by speech-based assistants on your favorite smartphone. So how did we get to this state of the art? The theme of facilitating computers with knowledge about the general world is very old in AI. It goes back to the 60s, 70s. But it took until the late 80s that for the first time, this project called Psych actually built a knowledge base of notable size. A team of knowledge engineers led by Doug Lennett handcrafted logical assertions like these. In parallel, Miller and Fellbaum, computational linguists, came up with WordNet, where they modeled words and word senses, capturing both synonymy as well as the opposite, homonymy, where the same word, like player, can have different senses depending on context. And they modeled specializations and generalizations in a taxonomic concept space. Both of these were completely handcrafted endeavors by small teams, so they were inherently limited in scope and scale. Then Wikipedia came along, and this became a game changer, because for the first time, a lot of human knowledge was brought into a single website and represented under a uniform format, the Wiki markup language. It was still meant from humans for human reading, not comprehensible by machines, but it was an opportunity, and that opportunity was taken by these three early projects, two academic, including ours, Iago, and one commercial. And Freebase got acquired by Google and formed the catalyst of the Google Knowledge Graph. There were other industrial players early on, like Wolfram Alpha, and then all the usual suspects, the internet giants, joined that technological trend as well. Today, there's also large knowledge graphs in industries other than the internet. Bloomberg is finance, Zalando is fashion retail. There's a number of projects in the health domain, and there's new academic players on the block as well. Major use cases, you already saw semantic search and question answering. We can further extend this into language understanding, like recognizing and disambiguating named entities in text. Distance supervision for machine learning tasks is another direction. And the entity linking often enables more advanced text analytics. This holds especially for vertical domains. The largest publicly accessible knowledge base today is Wikidata, 100 million entities, 1 billion facts. Our own project was always smaller in scale. We paid emphasis to very high quality, near human quality. And industrial knowledge graphs are even 1 or 2 orders of magnitude larger. So there is potentially at least a scalability issue. And our own group was actually concerned with this 10 years ago when Thomas Neumann was a member of our team. So we looked at how to efficiently index and query the knowledge-based content, which is typically represented in the form of these subject, predicate, object triples, following the RDF data model. Thomas came up with this very cool idea that we would aggressively index the single table by having indexes on all kinds of permutations of the subject, predicate, object components, including indexes on the projections. On first glance, this looks like a big space explosion, but actually the right compression techniques tame it down quite nicely. Moreover, what this gives us, the great benefit that we get here, is that the query optimizer now has way more degrees of freedom and can pick merge joins as the favorite option way more often. And merge joins by their sequential access pattern and locality are often a lot more efficient than any other choices for the execution plan. Needless to say, we were not the first to discover this general line of thinking. We were highly inspired by column stores, Martin's work, which were already a big success back then. We published this in the VLDB 2008. The same conference had a RDF related paper by Martin's group as well. Moreover, what's noteworthy is this was the first VLDB where the publications, the papers, appeared in this journal, Proceedings of the VLDB Endowment. I happened to be the president of the endowment back then, and Martin was a member of the board of trustees. And it was actually Martin who originally suggested this new kind of publication venue. He called it the paper fishing pond. Later, we found a more politically correct name, calling it Proceedings of the VLDB Endowment. How do we build knowledge bases? Knowledge is created only by humans, but they leave it in, on the internet. They leave digital footprints on the internet, structured data sets, but especially unstructured contents, like scientific publications, books, essays, news articles, and so forth. And what we can do with algorithms and machine learning, we can try to identify what I call cornerstones of a knowledge base, namely the individual entities, people, places, products, and so on. And for example, here we can identify Johan Cruyff, legendary Dutch footballer, Ajax Amsterdam, and the European Cup, now called the Champions League Cup. And we can distill these entities out and place them in the knowledge base with semantic class organization and with inference of relationships. Cruyff played for Ajax Amsterdam, and Ajax won the Champions League 3 times in a row in the 70s. So once we have a core of such formally represented machine knowledge, we can do a better job in interpreting noisy, vague, and ambiguous web content. And this way we can acquire more knowledge, deeper knowledge, and better knowledge. I wanted to call this architecture knowledge distillation, but the term data distillery was already taken by Martin's company. So we settled for knowledge harvesting. The methodology for doing this, for the acquisition or extraction, subsumes a variety of techniques. Handcrafted patterns and rules go a long way. There's pattern induction from examples, fully supervised deep learning, and also logic-based reasoning plays a role. I recently completed a comprehensive survey on this field. Here's the URL in case you are interested. Now, I want to give you a flavor for some of the techniques that we developed back then. So one is AI flavored. Suppose we need to populate the knowledge base relation has won. Which awards have people won? We start with seed facts from an initial knowledge base, the core knowledge base, and these seeds, maybe we get them from handcrafted, very conservative rules and patterns. So Adele won the Grammy Award, Mike won the Turing Award, and now we can search with these entity pairs in web contents, in large text corpora, and identify patterns that connect them. So we might get X received Y, X was honored by Y, and so forth. Next, we can search with the patterns and then identify entity pairs that are connected by the patterns, getting Leo winning the Oscar, Tiger, the PGA Golf Championship, Martin and Natasha, the Carter Award. I give you only first names on this slide for privacy reasons. We can iterate this further, and now we get these patterns, more patterns. Some are shaky, like extremes of Y, and then we get these fact candidates. Natasha won the Grammy, Martin the golf championship, Patrick the Tour de France, and Gustavo was honored by the Pulitzer Prize. Now, I give you a very simplified picture here. Of course, we can strengthen this by deeper computational linguistics, by deeper statistical inference, or by using deep neural learning. But the take-home point is that this technique by itself is very good in getting high recall, but you won't get super high precision in the 90%. So we need something else, and we developed that something else, and this is database flavored. So we call it knowledge curation, or maybe knowledge base cleaning, like database cleaning. The key point is to apply consistency constraints, a traditional asset in database foundations. Suppose we have these fact candidates, which are noisy. So we have 4 for the has-one relation, but also some noisy type triples. And now we impose these constraints. If someone has won a science award, that person must be a scientist. For sports award, you must be an athlete. For music awards, you must be a musician. And then we postulate that scientists cannot be athletes and they cannot be singers either, simply because scientist is a serious profession. There's no entertainment involved. So now what we do is we combine these two sites. So the fact hypotheses are plugged into the constraints, and this produces a large set of propositional logical formulas, so-called clauses, no variables anymore. In the application setting for us in knowledge curation, we would consider millions of such clauses. This is called grounding. You see examples here. And now this large set of clauses is almost certainly bound to be inconsistent, simply by the noisy process for getting the fact hypothesis, and also because some of the constraints might actually be soft constraints, tolerating exceptions. But what we can do, we can identify a large subset that is by itself consistent, a high quality possible world. And we can do this computation by different means. Machine learning has been brought here to this problem. We actually reduce it to a classical computer science problem, weighted maximum satisfiability, a variant of SAT, satisfiability, which is the classical NP-hard problem in our field. But there are very good approximation algorithms which you can tailor to this specific setting. And we even came up with distributed scale-out approximations. So in this example, the reasoning, the constrained reasoning would eliminate that Martin won the golf championship. Sorry, Martin. And Natasha should focus on her science career and forget about music. So in the last part, I want to come back to a database theme. I call this entities with quantities. It's motivated by this major challenge. Knowledge bases, as the name suggests, should also support knowledge workers, like analysts, media, market, financial analysts, journalists, data scientists from all fields. And these people often need to identify entities or semantic classes and their instances, group them into subsets, and then aggregate over quantitative measures and compare. Examples: marathon runners with the most races under 2 hours, 10 minutes, electric cars with the best range to energy ratio, antivirus drugs with more than 10,000 patients in clinical trials. These are tough. They would be easy if we already had the right contents in a structured knowledge base. But then knowledge bases like Wikidata, for example, they are rich in the entities of interest. So this part is covered, but they're very sparse and poor on the aspect of the quantitative properties that we need to aggregate over. The web has all the data, but it's spread across many sites in all kinds of noisy formats, and search engines are pretty useless. So the challenge is to augment a knowledge base with a rich set of quantities. This is one direction, and the other direction is to enhance search engines to support these kinds of analytic queries. And we approached the latter. This is very recent work, ongoing research actually. What we did is we settled for a somewhat more modest goal, which is more tangible. Namely, we identified this fragment of queries called quantity queries or quantity filter queries, which can be seen as a fundamental building block towards the more expressive analytics. Runners with a marathon under 2 hours, 10 minutes, musicians worth more than 100 million euros, hybrid cars with battery range above 50 kilometers. Again, they are not answerable from knowledge graphs because of the low coverage. So we need to extract answers from web sources. Note that these queries are different from quantity lookups like these, where an entity is given and we just need to look up the quantity. Knowledge graphs don't do this for lack of coverage, but search engines actually are not bad at this. Another remark is that I actually had an encounter with somewhat related work in 2016. I was a secondary and external reviewer for this very nice dissertation carried out here. So how do search engines do? What is JC worth? Works beautifully well. But then this is a quantity query in my definition. Wrappers worth more than $200 million, back to 10 blue links and very mixed quality pages. This is what we did, and there's AI inside. So we decompose this kind of queries in a smart way, and then we extract answers directly from text. I find it interesting that 50 cent is worth more than $150 million. We do the unit detection and the unit conversion on the fly. So this is done by automatic extraction of quantity facts from web text by deep learning. Now, finally, a database theme again. So we also tapped, this is actually ongoing work, not even published. We tapped into web tables, ad hoc tables embedded in web pages, spreadsheets, JSON files, and so forth. And here, the sports domain is actually richly covered by these kinds of tables. And for this query, footballers who transferred for more than 50 million euros, we get these high quality results. And note that we identify the right column of interest with a header fee and match it properly to the query. So this concludes the talk. Wrapping up, I presented my own scientific journey, some bits and pieces from databases to the web and AI, but revisiting my original field quite often. Actually, I would say I never left this field. The notion of databases has changed over time. The modern interpretation subsumes all kinds of non-standard databases like ad hoc tables, data lakes, and so on. And in that sense, my main work on knowledge bases and knowledge graphs also can be seen as falling under the database theme. Martin Kersten has been a leader in this broader field of modern database understanding. He started in traditional core databases, database machines, parallel systems, performance-driven database architectures, huge impact through column stores, but moving all the way to modern data science. One of his unique traits that I admire very much is his ability to think outside the box, come up with very unconventional, fresh ideas, turn them into success, and make impact this way. Thank you very much, Martin, for decades of inspiration, courage, persistence, and impact. I wish you all the best for the now more relaxed second half of your life. Thank you, Martin.